right, how you guys doing today? Good? Cool. So, let's go through some of these practice problems here. We are asked to design a solar array using 6-volt panels that produce 50 milliamps each. And we want to create an array that produces 18 volts total and 100 milliamps, right? So let's see how we can do that. First of all, let's talk about the voltage. We want to get up to 18 volts. So we want to put panels in series or parallel to increase the voltage? Series, yeah, exactly. So if each panel produces 6 volts, how many do we need to create 18? 3, that's right. So start with 1 down here. I'm going to draw the panel, each panel like a battery because they function like batteries. And we just connect them end to end like that, right? So we'll call this bottom part of the array 0 volts, and we know that the voltage is constant along any wire. So if we have 0 volts over here, we have 0 volts along this whole wire, right? And then this panel creates 6 volts and 50 milliamps. So we're starting at 0 volts and we go up by 6 volts. So how much voltage do we have there?
6.
6 volts, exactly. So then we go up by another 6 volts when we cross the next panel. So how much do we have there? 12, perfect. And then 6 more takes us up to 18 volts at the top. So now we've created the 18 volts that we want, but how much current do we have flowing out of this column of panels? 50 milliamps, exactly. So what can we do to produce the 100 milliamps that we want?
Run 3 more in series or serials parallel to that.
Well said, yeah. Yeah, exactly. So we can set up another column right next to our first column. And if we have 3 panels in this other column, we'll have 18 volts there, just like we did before, which is what we want. And then this other column will also contribute 50 milliamps of current. So each column is contributing 50 milliamps of current, and when those streams join together, we have a total of 100 milliamps coming out, and that's what we want, right? And you guys remember that when we measure the voltage and current from our panel, we do it with a meter right here. We do this whether we're measuring one panel or whether we're measuring the entire array. When we have the meter set up to measure current, the meter acts almost like a wire. So this circuit behaves the way that it would if you had a straight wire from power to ground. What do we call it when you have a wire straight from power to ground?
Short circuit.
A short circuit, exactly. So this meter is measuring the amount of current that would be flowing through a short circuit. So we call that the short circuit current when we measure it this way. Okay? If we leave the meter in the same place but we change the mode to voltage, the meter changes its resistance to be very, very large. In fact, it behaves almost like an open circuit, like there was no connection to our array at all. So the meter is actually measuring the amount of voltage that you would have if the array was not connected to anything, if the array was an open circuit. So we call that the open circuit voltage. So we measure the short circuit current and the open circuit voltage for solar panels and solar panel arrays. Okay? Questions about that? So then let's move over and do this other practice problem. So in this case, we're using 10-volt panels that produce 200 milliamps each, and we want to make 20 volts and 400 milliamps. So how many panels do we need in series?
2.
2, exactly. So 10 volts, 200 milliamps. So if we have 2 of those in series, that produces 20 volts and 200 milliamps. So we need another column just like that next to it. So now each column is contributing 200 milliamps, and when those streams combine, you end up with 400 milliamps and 10 volts. 20 volts too. Any questions about that? Okay, cool. So that was a little bit of solar panel math. Let's talk about a one sun concept, okay? Solar panels absorb their energy from the sun, so we need to talk a little bit about the sun when we're talking about solar panels. So what is one sun? Can anybody remember what that describes?
1,000 watt.
Yeah, about 1,000 watts per square meter, right? So that's the amount of energy that you would get if the sun was directly overhead on a clear day. So you can use that figure when you are trying to determine how much energy a solar array will absorb. You can figure out how big your array is and how much sun you're going to be getting, whether you're facing directly towards the sun or at an angle. And you can use that to figure out how much energy your array might absorb. What were some of the things that could affect solar panel efficiency?
The angle, the weather, how clean it is.
Yeah, absolutely. All of those are very true. The angle, you guys saw when you were holding your panels out in the sun that you had to face it straight towards the sun, right? Just point it a little bit in either direction and the voltage and current would go way down, right? And you guys were lucky you got a pretty clear day out, so you didn't have to deal with cloud cover too much. But if you were out there and there was just a small cloud passing over the sky, you would see the energy dip way down as well. And yes, like you said, any dirt or debris that builds up on the surface of your panel can really cut down on the energy that it absorbs as well. So you want to keep them clean. Temperature is another big factor, right? We talked about how cold temperatures can increase the efficiency of your panels, so you need to keep that in mind too. So any questions about solar panels or solar panel math? Okay, cool. So then let's talk a little bit about today's agenda. The first thing I'm going to tell you a little bit about is a field trip. We've got a field trip scheduled for Folsom Powerhouse, so I'll talk about that in just a minute. We already did the review. Today's lecture is going to be on Watt's law and power. So we're going to talk about what power is. We're going to talk about how Watt's law describes power, and we'll talk about several different forms of Watt's law. We'll go through a couple of examples of how we can use Watt's law, and then we'll do a preview of today's lab. Today we're going to build a circuit that actually uses light bulbs. So you're going to get to play around with a little board like this, and you're going to hook it up and you're going to measure the current and the voltage through each of these lights, and then you'll calculate the power that is being used by this circuit. So we'll talk about that. Any questions before we get started? Okay, cool. So then let's talk a little bit about the Folsom Powerhouse field trip. Anybody been to the Folsom Powerhouse before? Okay. Yeah, so it's a pretty cool place. It's an old powerhouse up in Folsom. It was started in the 1800s. It was one of the first powerhouses in the country, and it ran until the 1950s, I think. After that, they shut it down and they turned it into a museum. And so now we can go up there and we can walk around, and it's really cool. They have some really neat old power generating equipment up there. You can get up close and personal with it. You can really see giant generators. You can get up close. You can touch them. You can see all the controls that they had. You can see the facility that they built. You can see how the water flowed through it to run everything. So it's a really neat place. They have a tour that they do specially for our class. So we'll have a docent who's going to lead us around and tell us everything there is to know about the place. It's going to be on October 11th. It'll run from 10 a.m. to about 11:30. So that's during our normal class time. So you guys won't have to come to class today, or that day, right? So that's always a good thing. We'll just meet up at the place. I'll give you a map and directions when we get a little closer. So you'll meet there. We'll try and get there about 15 minutes early so that you have time to park and everything, and we can start the tour right on time. You guys will have to get yourselves there. We're not going to do a bus or anything, so I know. Yeah, right. So it'll be up to you to get there, but I will give you a map and tell you how to do it. It's not hard to do. It usually runs about an hour and a half, so that should be enough time for you guys to get up there, to do the tour, and then come back for any classes that you might have starting around noon, when this class would normally get out. So it's a really cool opportunity. I think it's going to be a lot of fun. We've done it many times before, and it always turns out pretty well. So I'm looking forward to it. Any questions about that? Okay, cool. So then let's go on and do our lecture. Let's talk a little bit about power and Watt's law. Oh, for homework, I'd like you to take a look at the Watt's Law quiz, which is on Canvas. This is one of those quizzes that you can take over and over again. It's for practice. It'll help you, it'll help me to understand where you guys are. So please try that out. You should know enough to give it a shot after today's lecture. And then also please read pages 89 through 93 in the textbook. These talk about series parallel circuits. So far in the lecture we've talked about series circuits and we've talked about parallel circuits by themselves. Next time we're going to talk about circuits that include series and parallel elements in the same circuit and see how those work together. So please read pages 89 through 93 to prepare for that. That'll give you a little bit of background. Okay. All right, so let's talk about power and what is it. Okay? So we've talked about electricity being like water in the past, right? Well, we're going to use that analogy again today to help us understand power. So, if you think about water in a pipe flowing out and hitting a water wheel, then power is how much that wheel turns. Okay? Power is the work that electricity does. Right? So, if the water is flowing out of this pipe and hitting the wheel, it would be how much it's making this wheel turn. Okay? So we can imagine a couple of different scenarios, right? We can imagine that we have a lot of water flowing out of this pipe, but it's flowing out very slowly, right? So the amount of water flowing out is like the current. So if we have a lot of current, but it's flowing out slowly, the water wheel is going to turn, but not very much, right? It's just sort of going to spin a little bit. So the amount of water is current. Now we can imagine another scenario. We can imagine that the water is flowing out really, really fast, right? But the pipe is really small, so there's only a little bit flowing out. So it's shooting out really hard, but there's only a small amount of it. So again, the water wheel is going to turn pretty slowly, right? So that the pressure that the water is coming out, that force, is voltage. So if you have a lot of pressure, but not a lot of water, the wheel is going to turn slowly, right? If you have a lot of water, but not a lot of pressure, the wheel is also going to turn slowly. You really need both. You need a lot of water and high pressure to make that wheel spin, right? Spin really fast. So you need both current and voltage to do the work that you want. And that's really what Watt's law says. Watt's law says that the power, the amount of work being done, equals current times voltage. So if you have high current and high voltage, you have a lot of power. If you just have current or voltage, you have a high current but low voltage, that's going to be small power. High voltage but low current, that's also small power. So you really need both current and voltage to do the work. Okay? So that's the essence of Watt's law. Now we can write this a couple of different ways. We can write it almost the way that we wrote Ohm's law to make it easier to use it. So we can say, for Watt's law, we can write it like this: P, I, and V.
Some of them have a square.
Yes, yeah, so we'll see that in just a minute. We'll see that there are actually other forms of Watt's law as well. So, in fact, yeah, we can talk about that right now. So, we can use this form of Watt's law if we know the current and the voltage and we want to find the power. Or we could use it if we know the power and the voltage and we want to find current, or the power and the current and we want to find voltage, right? And if we know any two of these three things, we can use Watt's law to find the other one. But sometimes we don't have all of these things, okay? I'll give you an example. Say we've got a resistor here, and this is one of those resistors you pull out of the bin in the lab over there. Those small ones. Almost all resistors are rated in terms of the amount of power that they can handle, okay? And that's because these resistors turn power into heat. So if you put too much power into them, they're going to heat up too much, and they can burn you, and they can actually catch on fire eventually if you leave them there for too long. So all the resistors are rated for power. Those small resistors that you look at are usually about 1/4 watt. Okay? If you get bigger ones, they can be a half-watt resistor. Even bigger ones can handle a watt, but those little ones that you see in the bin are quarter-watt resistors. So imagine that you pulled one of those out, and it was 2 kiloohms. And you wanted to find out, well, how much voltage could I hook up across a 2 kiloohm 1/4 watt resistor before that resistor burns up? Well, no, I mean, we've definitely put more than a half a volt on the resistors.
Divide.
So you might think about Watt's law, because this is involving power, and Watt's law has to do with power. But if you just look at this form of Watt's law, we can't really use that just the way that it's written. Okay, so we actually have other forms of Watt's law also. There are 2 other forms that we care about. We say power equals I squared times R, and also power equals V squared divided by R. Okay? And these formulas are all written out in a nice table for you guys. And that's in your lab books. It's on page 57. Okay? It's along with that powers of 10 table. There's this circle that shows all of the different forms of Watt's law. So you don't have to memorize these. You can use them on the table. But let's get back to our example here. We're trying to figure out how much voltage we can put on this circuit if we have a 2 kiloohm 1/4 watt resistor. So we look at our different forms of Watt's law, and we see that here we have resistance, power, and we're trying to find voltage. So what we have to do is we have to look at which of these formulas includes resistance, power, and voltage. And then we can use that one. So in this case, this formula includes power, voltage, and resistance. So if you guys are, so we can use that over here. We say power equals V squared over R. If you guys have done a little bit of algebra, we can rearrange that. If you're not comfortable with algebra, that's fine. You can just use one of the formulas from the table there. So we're going to go the algebra route here on the board. So we say V equals the square root of P power times resistance. Okay? So in this case, that's the square root of 0.25, yeah, times 2,000, or the square root of 500. So does anybody have a calculator?
22.36.
22.36. So the maximum voltage that we could put across a 2 kiloohm 1/4 watt resistor is 22.4 volts, approximately. Okay. So,
So we have to convert the quarter to the decimals.
the 1/4. No, you don't. I mean, a quarter times 2,000 is the same as 0.25 times 2,000. Either way is fine. All right, so that's one example of Watt's law. Let's look at it a different way. Let's say that we have a resistor here, and we've got say 2 amps and 3 volts here. How much power would this resistor be dissipating? Yeah, exactly. We can use the Watt's law formula up here. We look, in this case, we have current, voltage, and we're trying to find power. So we can use this form of the law. So we say power equals current times voltage, right? We just cover up power. So that's 2 amps times 3 volts. So power equals 6 watts. Okay. So we would need a big resistor for that one, right? So, any questions about Watt's law? Okay. Should I go over one more example, or are we good? We're good? Okay, so you guys will have, yeah.
Can you go one more for when you find the I square?
Sure, yeah, sure, we can do I squared times R. So, we could say that we've got a 500 ohm resistor here that's also, well, maybe this one's a bigger one, right? So we'll call this one a 1/2 watt resistor. And I might ask, what is the maximum amount of current that this resistor could handle? Okay. So what we can do is we see that we have I, R, and P here. So we look for the formula that includes I, R, and P. So that's this formula up here. So we need to solve for I. So we say I squared equals P over R. So I equals the square root of P over R. So that is square root of 0.5 over 500. So that's the square root of 0.001, right? So what is that?
0.0316.
So 0.0316 amps is the amount of current that this could handle, or about 32
milliwatts.
milliamps. Yeah. Yeah.
So that watt, is that be anywhere? It's not like in this specific place?
I'm sorry.
When like you see that it's 1/2 watt,
Yeah.
so you just put it anywhere, there's no specific place to put
Oh,
it?
when I'm drawing the diagram?
Uh-huh.
I wanted to indicate that it was for this resistor.
Mm.
Since there's only one resistor, it's not really critical exactly where you put it. You would just want to put it somewhere near that resistor on the diagram. Yeah. Other questions?
That 1/2 watt is just, you're talking about how much the resistor can actually handle.
Yes, yes. And that's usually a rating that you can find for a particular component. Yeah. Okay, cool. So that was a little bit about the different forms of Watt's law, and we did a couple of examples using those forms. So now I want to talk a little bit about today's lab. So like a lot of other labs that we've done in the past, this lab consists of some multi-sim and some hands-on. So we'll start with the multi-sim, and then we can move and talk about hands-on in just a minute. Okay, so we're going to start off in the ET302 directory, and we're going to go to L09 Power Lab here. We're going to start off with Watt A. So the first part of the lab is about measuring current and voltage, and then doing the Watt's law calculation to get power. So we remember power is current times voltage. So you'll measure both of those things, and then you'll multiply them together to calculate how much current you should be seeing. Or I'm sorry, how much power you should be seeing. And then you'll check your power that you calculated against the power that's measured in the lab. Okay. So you're going to set up a circuit like this. We can run the circuit, run the simulation, and that will measure the voltage across the resistor and then the current through the resistor. And we said that power was voltage times current, so if we multiply these two together, what power should we be seeing?
100.
Yeah, 100 watts. And then we can look at the meter, the simulated meter on top, and see that our calculation matches up with the measured value here, 100 watts of power. So you guys will be doing this and recording your results in your lab books. So there is a table that you're going to fill out. You'll write down the battery voltage, the resistor voltage and current, and then you'll multiply the two together to get your calculated power, and then you'll write down the meter power as well and check that your calculation matches what's shown on the meter. Okay? So you'll do that for several different values of the resistor. Part 2 is very much the same. You're going to be checking that your calculations match the meter. But in this case, you're going to be doing the calculations using the I squared times R form of Watt's law. So you'll measure the current, and you'll square that and multiply it by the resistance to get the power. And then you'll check to see that that matches the measured meter power as well. And the third part is very much the same, but you're going to be using the V squared divided by R form of Watt's law. So you'll be doing the calculation of power 3 different ways and checking that it matches the measured meter power in each case. All right? Any questions about that part?
Which page is it on?
It starts on page 93. Other questions? All right. Then, after you do the multi-sim part, you're going to move on and you're going to build a real circuit hands-on. So let's talk about that. This is the circuit that you're going to be building, and you'll notice that it involves 2 light bulbs. Okay? So you guys are going to be using a board in class that looks like this. It's got 3 light sockets on it, and you can screw the little light bulbs into the sockets. We store the light bulbs separately from the board because otherwise the light bulbs just get crushed if they get thrown in with all the boards. So when you go to the lab, you'll want to grab a board and also 2 light bulbs to fit into it. Okay? So let's talk about how to construct this circuit. When I construct circuits, I like to just go through the diagram piece by piece and build it up as I go. So that's what I'm going to do here. I'm going to start with the power supply here. And I see that the power supply has 2 wires coming out of it. One wire is connected to the top of L1, and the other wire is connected to the bottom of L1. So that's what I'm going to do. I'm going to take my leads from the power supply here. I'm going to connect the positive lead to the top of L1 here, and the negative lead to the bottom of L1. Okay. So now we've constructed this part of the circuit. Now I see that the top of L1 is connected to the top of L2. So I'm going to make that connection there. To do that, you're going to use a new type of wire that I don't think you've seen before. This is a little wire that has alligator clips on the end. You can get these wires from the little rack next to the electronics tool room window at the back. You can just grab as many as you need. And the little clips are called alligator clips because they have little jaws that look like alligator jaws. All right? So we're going to clip one side of the wire to the top of L1 and the other side of the wire to the top of L2. So we've now made this connection from the top of L1 to the top of L2. The last connection that we need to make is from the bottom of L1 to the bottom of L2. So we're going to take another one of these wires with the alligator clips and connect from the bottom of L1 to the bottom of L2. And that's our whole circuit. Okay. So that's the first part. Once you've built the circuit, you can plug it into the power supply and set the power supply to 12 volts and turn it on, and then your lights should light up. Okay? And then you'll be measuring the voltage and the current at various places in this circuit. So let's talk about how we're going to do that. Everybody's going to get a multimeter, just like you have before. You remember when you set up the multimeter, the black lead always goes in the common slot, and then the red lead moves around depending on what type of measurement you're making. So we're going to start off with the voltage, so we're going to put it in the far right-hand slot there. And we're going to turn our dial into the voltage part of the meter. Okay. So, you guys remember, is voltage a destructive measurement or a non-destructive measurement? Non-destructive, right. Voltage is the easy kind of measurement because you don't have to take the circuit apart at all. You just touch the leads to wherever you want to measure the voltage and you can measure it right off. So, first of all, it asks us to find the voltage across lamp VL1. So to do that, you just touch the leads of your meter to both sides of L1, and then it shows you the voltage right there on the meter, right? And nice and easy. You do the same thing for L2. Okay? So no problems there. It also asks you to measure the current. Now, current is a little bit trickier, right? Current is a destructive measurement. You have to partially deconstruct your circuit so that you can put the meter in series and all of the current flows through the meter and gets measured. Okay? So, when we, let's talk about how to do that, right? First of all, we have to set the meter into current measuring mode, so we're going to move the little red lead over into the current measuring hole there, and we're going to turn the dial into the current measuring location. And now we want to set, say for instance that we wanted to measure the total current for the circuit. Okay? So that would be the current flowing into the circuit from one of these long leads from the power supply, right? So we want to measure the current flowing through this power supply lead. So what we want to do is we want to break the circuit apart at the location where this power supply is coming in. Okay? So when we do that, we're left with sort of two dangling ends of the circuit, right? It's like you ripped a rope in half. You would have two ends, right? So same thing happens. You rip the circuit in half, and you've got two ends, right? One end is this little black alligator clip that I'm holding in my hand, and the other end is where it used to be attached. So that would be this post, right? So what you're going to do is you're going to take the two leads from your meter and connect them to those two dangling ends of your circuit. Okay? So one lead from the meter is going to go to one side, and then the other lead from the meter is going to go to the other dangling end, which would be that post. And when you hook up the meter like that, you are able to, the meter is in series with this long line from the power supply, and so the meter is now measuring all of the current that is flowing out of that wire. Okay? So when I do that, I'm getting, yeah, so you'll do that and you'll measure how much current you have, right? When you're done, you should take things apart and put the circuit back the way that it used to be, and then you can measure the current in another part of the circuit. Okay. So, any questions about how to measure voltage or current? Okay, cool. So that is really what I wanted to say about the hands-on part. You'll be measuring the voltage, you'll be measuring the current, and then you will calculate the power of each lamp and of the entire circuit using Watt's law. And then the last part of the lab, you will build a circuit on a breadboard. And this circuit is not too complex. It has a single power supply and a single resistor, and you'll be measuring the voltage across that resistor and the current through that resistor, and then calculating the power dissipated by that resistor. Okay, so any questions about that? All right, then let me take attendance and